All right, so this is 2.7, which is linear, which means line, and quadratic systems, which is your parabola. So it's talking about how lines and parabolas can intersect. All right, so how many solutions? The first question up here is how many solutions can there be for a linear quadratic system? So we're asked about a simple system here, okay? How many real solutions does the system x squared, y equals x squared, and y equals 2x have? That's not a hard thing to do. Y equals x squared is a mother function. She has coordinates at 0, 0, 1, 1, and -1, +1. She looks something like that. Y equals 2x is the next thing I'll graph. She crosses the origin at 0, 0. Remember mx plus b. And she rises 2 and runs 1. And she would look something like this. So it turns out that this has two solutions. Now, I was not asked to determine them, but she does have two solutions. She does. This intersection up here should be at 2, 4. But she does have two of them. Let me see if I removed a question or not. Okay, good, I didn't. Determining number of solutions. And the question is here is how many solutions can there be for a linear quadratic system? So how does modifying the linear function affect the number of solutions? So let's just go ahead and do a couple of graphs. We'll do y equals x squared. Obviously, that one's not going to change. Looks something like that. And let's make this a, I don't know, a -8. 1, 2, 3, 4, 5, 6, 7, 8. And they would rise 2 and run 1. If you change b in such a manner, we discover that y equals x squared and y equals 2x minus 8 have no solutions. So by moving that line up and down, you can directly influence the number of solutions that these two things have. There is a way to get just one solution out of this thing. And I believe it is if you make it y equals 2x minus 2, probably. Maybe -1, yeah. We're going to graph x squared and y equals 2x minus 1. Now 2x minus 1 would cross the x-axis just once, and it would rise 2 and run 1. I guess it still might have two solutions. But the big thing here is that when you talk about the intersection of a line and a quadratic, they may have two, one, or no intersection solutions. That's the big deal. I'm kind of tired and I don't want to write out all the models. The notes aren't supposed to be that time consuming. All right, how can you use substitution to solve this system? So if you'll notice, the first line is y equals 3x squared plus 3x minus 5. And the second line is 2x minus y equals 3. Well, you can literally just use straight up substitution property, and you can take all of this and you can put it right there. And that's what we're going to do. It's called substitution. So I am going to replace that y with the stuff above it. And remember, there's a minus y, so it needs to be included. It's a golden rule. Two or more things in math you should probably wrap. And it still equals 3. Don't forget about that piece. And then we're just going to clean it up with a distributive property. We're going to combine like terms. We'll see if it factors. I don't know. It might. Don't forget about your distributive property. A lot of kids like to forget about that. It's always little things that get kids. It might be the arithmetic, it might be the distributive property, but it's little things that hold y'all back. And it's why you can't do big things. All right, so like terms is up next. We've got a -3x. I swore I chose pen. We have a -3x squared. 2x minus 3x is minus x. There's a +5 and we equal 3. Now, I'm going to go ahead and one-side it. I'm going to subtract 3 from both sides, and then I'm going to do another step. I personally, I like A to be positive. And it's a personal choice. You don't have to do it, but if the math teacher does it, there's probably a reason for it. And that's what she looks like. Assuming I have made a mistake. That's apparent. 5 minus 3 is 2, Milbrath. And that's what she looks like. Let's make sure I haven't made any other mistakes. It does not appear that I have. No, I'm good. What I'm kind of surprised at is I was given something that doesn't seem to factor. And this is coming from a textbook. So I'm really surprised that they didn't do anything here. So when I look at this one here, I don't believe she factors. Doesn't look like she does to me because it's a plus plus, and those are usually in 2 and 3 is going to make 6. It doesn't seem like it factors. What do we do last in here? We have done complete the square and we've done quadratic formula. This one does not lend itself nicely to complete the square because of what x is and dividing by 3. So we're going to use the quadratic formula. So x equals negative b plus or minus, I don't know why I wrote the b. B is 1. X equals negative b plus or minus square root b squared minus 4ac all over 2a. So this one works kind of the way I thought it would work. And that's what surprises me. So let me pause this real quick. I don't like that your textbook did this. All right, kids, so what we just discovered here is that either I'm a little bit stupid or I'm too tired right now. So I did make a mistake. I'm sorry about that. I'm sure that some of you have already figured out where my mistake was by now, but you didn't want to say anything. I wrote that 5 minus 3 was negative 2, and it's not. It's positive 2. Now, I still want a to be positive. So moving on from that, I'm going to do the division of a negative. And I'm glad that this happened because now I am very confident that it factors. And it does factor. I see it now. It's just a sign mistake. We got to be careful about those. And you don't have to factor, but it's quicker if you're good at it. So to make a 3x squared, we take a 3x and x. Signs are a big deal here. Let's put a 2 here and a 1 here. And the inside would now make 2x, and the outside would make 3x. Notice I want the positive x. The 2 is negative. So there's your signs. All right, so now we're going to use what we call the zero product property. So by ZPP, the zero product property, 3x minus 2 is a 0, or x plus 1 is a 0. So we'll add 2 to both sides. 3x is 2. We'll divide by 3, and x is 2/3. And here we just subtract 1 from both sides, and x is negative 1. Now, when you solve a system, give your answers as ordered pairs. When solving a system, you find x and y. That's just what you do. And it's not a hard thing to do. It would be easier to plug into the second equation as opposed to the first equation. It would be. And that's what I'm going to do. Everywhere I see an x, I'm going to become 2/3. So 2 times 2/3 minus y is 3. 2 times 2/3 is 4/3. And if we move it to the other side, it would become negative. So negative y equals 3, which is 12/3 minus 4/3. And that would say negative y is 12 minus 4, 8/3. And then you got to divide out your negativity. So y is going to be negative 8/3. And boy, I know I just lost a whole bunch of you right there. I know I did. But you have this ordered pair, 2/3 and negative 8/3. All right. Plugging in the negative 1 will be easier. Everywhere you see an x, you're going to be a negative 1. So twice a negative 1. Again, I'm looking at this line. Minus a y is 3. That's negative 2 minus y is 3. Add 2 to both sides. Y is 5. So y is negative 5. And this gives us the other ordered pair, -1, -5. Ta-da! It ain't that bad. Although don't make sign mistakes. All right, so we're going to do a try it. I'm not going to do both of them. I'm just going to do one of them because I don't really want to do all of them. We're going to use substitution. Again, we're going to put that right there. So I have a 2x. I'm taking away 3 or more things I do need to be wrapping. 2x squared minus 6x minus 8, and that would equal to 16. All right, do not forget to distribute your negative. So minus 2x squared plus 6x plus 8 still equal to 16. And combine our like terms. We'll have 8x's, and I know that's an issue for some of y'all. And on the last one, you know, what I did is I divided out the negativity. I'm not a huge fan actually doing that. I'm a shifter. I like to shift things around. It's just how I do it. I'll put the 0 on the left-hand side. That's going to make 2x squared positive. 8x is going to be negative, and 16 minus 8 is going to be, I believe, 8. And I'm going to just keep trying to factor, man. I'm going to keep trying to factor. So I have one of my commandments of math says, if you can pull it, pull it. Everything is divisible by 2. And now the question is, are there factors of a positive 4 that add to the negative 4 in the middle? And there really are. We have x minus 2 and x minus 2, and that works. So by ZPP, the only thing that matters is this factor, and of course they're the same. And I'm going to talk about them. This says x is 2. It happens twice, right? This is called a repeated solution. Kind of interesting. It's called a repeated solution, but it happens. It happens twice, oddly enough. So I know that x is 2. So once I have the x value, how do I get the y value? Well, I just use substitution again. Everywhere I see an x, I can become a 2. 2 times 2 minus a y is a 16. I'm going to do this one a little bit differently too, because again, I'm a shifter. I'm going to shift that there and that there. 2 times 2 is 4. You jump equality, you change your sign. And then 4 minus 16 is y, which tells us that negative 12 is my y value. And again, ordered pairs are nice. They are. So your solution to this system happens at 2, negative 12. Again, I'm just going to do the one try. I don't want to bore too much of your life with these things. It's the same thing. It's rinse and repeat. All right. Revenue for the high school band concert is given by the function y equals negative 30x squared plus 250x, where x is the ticket price in dollars. The cost of the concert is given by the function y equals 490 minus 30x. At what price will the band make enough revenue to cover their costs? So what they're asking in math speak is literally when is revenue equal to cost? So we have a revenue function. The revenue function is negative 30x to the second plus 250x. And we want to know when it equals 490 minus 30x. This is actually just using what we call the transitive property. That's all it is. The author of the textbook probably wanted us to set up a system of equations and use substitution. You don't always have to do substitution. You can use the transitive property. The reason I did this is because they were both equal to y, okay? And if you can see the transitive property, it makes things so much clearer. Let's put this thing in standard form. I am going to shift everything left. If I shift a negative 30x squared, to the right, from left to the right, it's going to become positive. I already have a negative 30x. Right next to it, I'm going to put a negative 250x. And 490 was already on the right-hand side. So let's combine our like terms. And notice they did not want you to actually solve for y. They just want x, which is the ticket price. A little curious if this thing factors or not. Everything's divisible by 10. I know that much. See if there's anything else that's more apparent to me. My brain is tired. So do 3, 28, and 49 have any common factors? They do not have any common factors. Does it factor? Yes, it does. It does factor. I know that you know that it takes a 3x and an x to create 3x squared. And factors of 49 are going to be 7 and 7, right? So now think about this. 7 times 3 is 21. 7 times 1 is 7. 21 and 7 makes 28. But I want a negative 28. Therefore, they're both negative. And that's okay, because guess what negative 7 times negative 7 is? It's 49. So now we're going to use ZPP, the zero product property. I know that 3x minus 7 is a 0. Or x minus 7 is 0. Now, we're going to talk again about a vocab word here in just a second. And there are teachers that would argue with me that this is not what it means, but it is what it means. If my keypad will work. If 3x minus 7 is 0, 3x is going to be 7. The opposite of multiplication is division, so x is going to be 7/3. Interesting. Which, by the way, in terms of dollars and cents, is going to be roughly $2.33. The others, and never mind. These are both valid answers. The other one is pretty simple. It's x equals 7. Now, the reason I'm putting in dollar signs is because this was the ticket price in dollars. So why are there two answers? Why are there two answers? You know, that's the question. Why are there two answers? Because it's a parabola, kids. Isn't it? Parabola go up, parabola go down. And at these prices, since we set it equal to 0, this is where we smash into the x-axis. All right? So what you really want is you want your price to be somewhere between these two things, because you want to maximize revenue. These people are only concerned with covering costs. But what happens in reality is at $2.33, you get a lot of people to come watch your show, but you haven't brought in that much money. At $7, you get some people to watch your show, but all you've done is cover your cost. You really want to be up here at what we call the vertex to maximize revenue. But that's break even, all right? In reality, somewhere half between is probably going to be, and that's exactly what it's going to be. Halfway between these two things is going to maximize the revenue, which is going to make profit. All right. Oh, inequalities. Inequalities are usually a complete disaster. They are really bad. To actually understand inequalities, you have to know how to graph or do number lines. And I've discovered that graphing works best, so I'm going to teach you via graphing. All right. We're going to use substitution. Well, let me pause and think real quick. Let's see if I should do this a different way. So I was a little torn on how I wanted to teach this, and I was looking at your textbook to see how the author wants you to learn it. And your author wants you to graph this by hand. As big a fan of that as I am, if I teach it that way, 95% of you would never be able to figure this out. I know that based on history. So what we're going to do is we're going to graph it with assistance of technology. We're going to graph with the assistance of tech. All right, we're going to let the calculators do a lot of this for us now. The graph with a TI-84, the equation needs to be, needs to be in the form y equals. We don't have equality, but we have something that's good enough, okay? So the only one I really have to change is going to be this one. We're going to do y greater than, solving for x, by the way, negative 4x plus 4. And then we're going to let our calculators take over. And I'll do my very best to explain it. That may or may not be enough. It may or may not be enough. We'll see. So I'm at y equals. That's where I'm heading. Let me make sure I've got stat plots off. You don't have to do this. This is just my calculator. I use it in other classes. All right, we've got negative 2x to the second. Don't worry about shading. We'll do our best to explain this here. Plus 12x minus 10, that's going into y1. y2 is going to be negative 4x plus 4. We're going to zoom 6. And hopefully it's enough. What we want to see here is we want to see both intersections. All right, so I'm going to have to play with the window here. I don't know if we've done that in this room or not, but I'm going to look down. I'm going to change my y max to be negative 20 and see if that's enough. Play along, by all means, play along. Or don't. It's what ifs. Oh, it still wasn't enough. Obviously, we could do this algebraically too, but it's not obvious when you're doing the algebra why it works the way it does. Try negative 30. I know I need to hurry up. I've only got 8 minutes for my next class, and if I don't finish this video in time, I have to start all over again, which is fine. I just wasted some time. All right, so I'm going to kind of get my version of a screenshot here of this. Let's apply some logic to it. Now, the first equation was about the parabola, the negative 2x squared. And it says less than the parabola, okay? That means below the parabola. The second equation was about the line, and it means above the line. What we're being told is that this is the solution space, okay? Now, here's the big deal. The big deal is what x values create this space. So we're going to have to figure out some intersections. I'm pretty sure that one's 1 and that one's 7 because I did some algebra earlier. And like I said, the problem with the algebra is unless you've done graphs for a while, it's not apparent why it works that way, so I don't want to explain it. But your calculator, and we've done this before in class, we can hit second trace 5, which is the intersect feature. And I'll go slow on the next one. Get close, press enter 3 times. There's an intersection at 1, 0, just like I told you it was. And let me go a little slower on this one. Second trace 5. Get our cursor close to the other intersection. Enter once, twice, thrice. 7, negative 24. The x values that create this are 1 and 7. And we always answer inequalities with inequalities. So what makes this true is for x to be stuck between 1 and 7. Anything between 1 and 7, and then there's an infinite number of things between 1 and 7, makes this true. Good stuff, right? We're not going to do this one just to say, well, yeah, we're not going to do this one to save a little time. Solve this system by writing a linear quadratic system and solve using the intersection feature of the graphing calculator. And this is something we've already done in class before. Solve this system by writing a linear quadratic system. So what they want you to do is they want you to consider this a y and this a y. So one of your equations is y equals 3x squared minus 7x plus 4. And the other one is y equals 9 minus twice x. And what we're going to do is we're going to put the first one in y1 and the second one in y2. And again, you need to play along with the calculator. Let me point something out here. But you're not going to do it. Prove me wrong. Milbrath told you that you can go to ti84calc.com and wait and see what shows up. It's a TI-84. Like, play along, kids. Play along. Anyways, back to what I had here. 3x squared minus 7x minus plus 4. And the other one is simply 9 minus twice x. Do a zoom 6, because if you were playing along with me on the last one, you've already got a different window setting. Zoom 6 restores defaults. And it's usually good enough. Usually. On this one, it should be. Boy, it's close, isn't it? Well, let's look up just a little bit. It's actually going to have to be, you'd actually have to have a y max of 11. I'm going to change it to 15. Pretty sure there's an intersection at -1, 11, but I could be wrong on that. And here's what I have. Nope. Got a little fast there. So solutions are simply where we intersect. And if you didn't play along last time, what we're going to do is we're going to hit second, trace, and we're going to choose intersect. We get the cursor close, and we press enter 3 times. So second, trace, 5 for intersect, get the cursor close, enter, 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 and there's the intersection. It's not pretty numbers. We'll just go 4 digits, -0.7033. Assuming I don't have a typo. And then 10.4065. So there's one system, there's one answer, okay? Now I will say that because the original equations didn't involve x, y, the only thing they want is the x value. What's the next one? Second trace 5. And a calculator is, sometimes required unless you learn some pretty advanced math. The other one is at 2.3699 with a y value of 4.2602. And again, what I was after here was not the y's, I was after the x's. But that's how you solve with the assistance of a TI-84. And that's where I need to be done with this lesson. Sorry I didn't have a lot of energy. Just kind of wore myself out about halfway through this thing.